Welcome back to the Deep Dive, The Learner. Knowing your robotics background and, your interest in where things are heading, especially this whole intersection with large language models,
Yeah.
well, we've put together a deep dive into some really fascinating recent work.
Yeah, exactly.
You mentioned wanting to understand how LLMs and transformers are, impacting robotics, maybe without getting too bogged down in the AI architecture details themselves. So
Mm.
that's precisely our focus today.
Absolutely. And for this, you flagged two, I think, really key papers. There's Interactive Robot Learning from Verbal Correction. The acronym is OLF by Liu and
All
colleagues.
right?
And then there's Yell at Your Robot, Open-Ended Instruction Following with Hierarchical Vision Language Action Models, which, well, the title says a lot.
It certainly does. Both seem to be tackling how robots can learn and sort of adapt using natural language feedback. It
Okay.
sounds like it could be a pretty big change for anyone used to, the traditional ways of programming robots.
It really could be.
So yeah, our mission today is basically to unpack how these systems use language, just talking, essentially to teach robots, fix their mistakes.
Uh,
We'll focus on the main ideas and, importantly, what this means for robotics, especially from your perspective coming from that field. So let's jump in.
Okay. So one of the big challenges, and this comes up a lot as robots move into less structured places like, our homes.
Right, outside the factory floor.
Exactly. It's this need for them to learn and adapt after they're already out there. The OLF paper really highlights this. When you think about typical robot programming or even imitation learning, there's often a ton of upfront effort involved.
Oh, totally. I mean, imagine trying to pre-program every single possible failure mode for a robot just trying to pick up a cup in a cluttered room.
Yeah.
It's almost impossible.
Right. And imitation learning helps, but you still often need these huge data sets of perfect demonstrations. What these papers, and OLAF in particular, are trying to get at is a more direct and intuitive way for us humans to guide the robot's learning. Kind of like how we teach each other, really.
Yeah, that makes sense. Like telling someone, no, hold it steadier.
Exactly like that. OLAF is specifically looking at learning from verbal corrections. It's such a natural thing, right? Someone messes up, you give them a quick pointer. The paper even kicks off with that example, a kid spilling water and being told, keep the cup upright next time.
Ah, okay.
That's the kind of intuitive feedback they want to build into robots.
And this is where it gets really interesting, I think, for someone with a robotics background learner. The core idea in OLF isn't just about the robot understanding the command in the moment.
Right.
It's that the robot can actually update its own control strategy, its visual motor neural policy based on what you said. So if you say, whoa, stop, move left a bit, it's not just a temporary fix. It's actually learning from that correction to avoid doing the same thing later.
Yeah, and that's a key step forward. Some earlier work used LLMs to get robots to follow instructions, which was already cool, but OLAF adds this learning piece. Without it, you might just be correcting the same mistake over and over again.
Yeah. Perpetual correction problem, yeah.
Exactly. OLAF wants the robot to actually get better, to become more self-improving just through us talking to it naturally.
Okay, so how does it actually do that? How does it learn from me just saying something? You mentioned a three-part process.
Yeah, basically three steps. First is the obvious part, user interaction. The robot tries to do something, say, grab an object. If it looks like it's about to mess up, you can stop it and give a verbal correction, like grab it more from the side.
Okay, simple enough.
Then comes step two, data synthesis. And this is really where the LLM plays a crucial role. OLAF uses the LLM to look at what the robot was doing right before you stepped in, and it combines that with your verbal feedback. The LLM's job is essentially to relabel the robot's actions during that brief moment before the intervention. It figures out what the robot should have done instead, based on your correction. There's a diagram, figure 1 in the paper, that shows this loop pretty clearly.
Relabeling the past actions.
Okay.
And you mentioned the pre-intervention region. That's just that little window before I react.
Exactly. The paper mentions humans usually react in about, 1 to 2 seconds. So it's that short period right before you hit stop or yell out.
Makes sense. That's probably where the error actually started.
That's the idea. OLAF focuses its correction right there. It's not trying to replan the whole thing, just fix the bit that went wrong. And the LLM acts as a kind of critic in this step. It gets fed info about the robot's state position, object locations, that sort of thing.
The kind of stuff you'd need from sensors in a robotic system.
Precisely. And it also gets a set of possible small adjustments the robot could have made at that moment.
Okay, so how does the LLM pick the right adjustment based on what I said, like move it right.
That's done using carefully crafted prompts. Figure 4 in the paper breaks this down. There's a system prompt telling the LLM its role, then a context prompt with background info, like a basic manual for the robot arm they used, a Franka Panda, and the original task instruction.
Gotcha. Setting the scene for the LLM.
Right. And then the crucial part, the action relabeling prompt. This gives the LLM the specific robot state at the moment of correction and the actual words you spoke, your feedback.
So context, problem, and the desired fix in plain English.
Exactly. So OLF proposes a few small potential changes, like tiny nudges in different directions or rotations for the robot arm. The LLM looks at these options, considers your feedback, move right, and picks the nudge that best matches your instruction.
Okay, that's clever. And then step 3, what happens with these LLM-suggested corrected actions?
That's the policy update. The robot takes this new data point, the problematic trajectory segment, paired with the LLM's relabeled correct actions for that pre-intervention moment, and uses it to fine-tune its internal policy. It uses imitation learning, basically learning from its corrected near misses.
And the results seem pretty promising, like a decent jump in success rates.
Yeah, they reported about a 20% average improvement overall, and importantly, nearly 18% improvement just from the verbal correction learning component alone, which is, quite significant.
To really suggest this isn't just a theoretical idea.
Definitely. And they also found, maybe unsurprisingly, that more specific feedback worked better. Lower the gripper slightly is probably more helpful to the LLM than just try again.
Makes sense. Did they look at different ways the LLM could suggest the fixes?
They did. They tried a few things like having the LLM generate whole new actions versus just editing the robot's planned ones slightly. They found that the best approach seemed to be letting the LLM act as a critic for small, one-dimensional changes added to the robot's original plan.
So guiding rather than completely rewriting.
Kind of, yeah. It seemed more effective in their experiments than having the LLM try to invent a whole new strategy on the fly every time.
And OAF isn't just a one-shot deal, right?
Mm.
You can do this correction cycle multiple times.
Absolutely. It can run through interaction, synthesis, update, repeat. It's very similar in spirit to interactive imitation learning algorithms like Dagger, if you're familiar with that.
Ah, okay. Where you iteratively get expert feedback.
Exactly. But here, the LLM, guided by your feedback, is effectively playing the role of that expert, pushing the robot's policy towards better performance over time.
Okay, that covers OLF. Let's switch gears to the second paper, Yell at Your Robot. The title alone suggests maybe a slightly different philosophy.
Yeah, it's a bit more provocative.
Right.
While OLF is about learning by fixing past mistakes, YY Robot is more focused on, let's say, continuous improvement and on-the-fly adaptation using language. It uses a hierarchical setup.
Hierarchical, meaning like different layers of control.
Exactly. There's a high-level policy that thinks in terms of language instructions, and then a low-level policy that actually executes skills based on those instructions.
Okay, so I'm not directly correcting the robot's motor commands, but maybe the instructions it's giving itself.
That's a good way to put it. The goal here is more about real-time adaptation. They use something called a language-conditioned behavior cloning, or LCBC, policy for the low level. Think of it as one network that knows how to do lots of basic skills, grasp, push, pour, and the specific skill it does is chosen by a language command it receives.
Like pick up the red block or move forward slowly.
Precisely. This makes the low-level system quite flexible. Now, the high-level policy's job is to generate those language commands autonomously, trying to break down a bigger task into steps, almost like a person would instruct the robot.
Okay, so where does the yelling come in?
The user feedback.
Right. When you provide a verbal correction, the yelling, it temporarily overrides what the high-level policy was suggesting. Your command goes straight to guiding the low-level policy for immediate effect.
So it changes behavior right away.
Yes, for immediate adaptation. But here's the crucial part for long-term learning. Those interventions, your corrections, are then collected and used to fine-tune the high-level policy.
Okay, wait. So the system learns from my corrections to give itself better instructions in the future.
Exactly. The high-level policy learns over time what kinds of instructions lead to success and what kinds lead to needing correction. It aims to get better at generating good instructions and even anticipating problems, so you hopefully have to yell at it less often over time. It's a bit like HG Dagger, if you know that, but operating over language instructions instead of low-level actions. That's really interesting. So it's learning how to be a better task planner or instructor for its own low-level skills. The paper mentioned different data sets.
Yeah, they use a base data set that's observation, action, language instruction, triplets, to train both policies initially. The low level learns skills from language. The high level learns to generate language. Then there's a correction data set, which is just observation, users, language correction. This correction data is used only to fine tune the high level policy, while the low level skills stay frozen.
Got it. And they tested this on some pretty complex tasks, right? Bag packing, trail mix.
Yeah, long horizon, fairly dexterous stuff. Bag packing involved putting different items into a bag carefully. Trail mix prep needed scooping and pouring accurately. Plate cleaning used a sponge to wipe a surface. All things that require a sequence of coordinated actions and dealing with variability. Figure 1 in the paper shows them nicely.
And did it work? Did the fine-tuning help?
Significantly, yeah. In bagpacking, for instance, the success rate jumped from something like 20% to 45% after the high-level policy was fine-tuned with user corrections. It shows this continuous learning loop really can improve performance through interaction.
Wow, that's a big jump. And you said the high-level policy even started generating its own corrective style commands.
That was one of the coolest results. After fine-tuning in the bagpacking task, it learned to sometimes tell itself things like, open the gripper wider, or wiggle if it sensed an object wasn't going in right.
Ah,
Or for plate cleaning, it would generate specific commands like clean the bottom left corner to guide the sponge. It's actually learning effective sub-strategies based on the feedback it received earlier.
so comparing it to OLF then, YA robot is more about real-time adjustments and this hierarchical learning,
Mm,
while OLF is more about post hoc relabeling of actions.
that's a good summary. YA robot adapts on the fly and it learns end-to-end from pixels, visual input, without needing that explicit textual state estimation that OLF used in its implementation.
And they also tried swapping in GPT-4V, the big vision language model, right? How did that go?
An interesting experiment. They tried using GPT-4V directly as the high-level policy. And while it could generate plausible-sounding language instructions, it struggled with the actual spatial reasoning and the physics of manipulation needed for these tasks without being specifically trained on robotic interaction data. It highlights that while these massive models are amazing, just plugging them straight into a robot might not be enough. They likely need more targeted training or integration for real-world control.
Right, the grounding problem. Understanding the physical world is different from understanding text and images.
Exactly.
Okay. So thinking about this from the perspective of the learner with that robotics background, what are the big takeaways here? It feels like a real shift.
I think it is. The major takeaway is this move towards more intuitive, language-based ways to teach and adapt robots. We're kind of shifting away from needing to meticulously define every single movement or gather endless perfect demos.
Yeah.
Instead, we're exploring how to leverage our natural communication language to guide robots in these messy, unpredictable, real-world situations where pre-programming everything is just, well, it's impractical.
But it's not like the underlying robotics knowledge disappears.
Right.
You still need solid control perception.
Oh, absolutely not. That's still fundamental. Think of these language methods as providing a new, much more user-friendly interface for refining the robot's behavior. The core robotics, kinematics, dynamics, control loops, sensor processing, that's all still under the hood. Language becomes the way we interact with and improve the higher-level decision-making or correct specific actions.
Okay, so recapping this deep dive for you, learner, we looked at two really cool approaches. OLF shows how robots can learn from specific verbal corrections using LLMs to cleverly relabel past mistakes.
And YAY Robot presents this hierarchical system that aims for continuous improvement, where language feedback fine-tunes a high-level policy that instructs a capable low-level policy.
Both really point towards, potential new era where robots are more teachable, more adaptable, using something as natural as speech.
Yeah, the potential for simplifying how we deploy and update robots in homes, hospitals, workplaces, it's quite exciting. Imagine just telling your household robot, hey, be a bit more careful around that vase next time, and it actually learns from that.
Of course, it's still early days. Both papers mention limitations like OLF needing that textual state representation or YAY robot needing a good starting low-level policy. These are active research areas.
Definitely challenges still to overcome, but the direction is fascinating.
So maybe a final thought for you, the learner, to mull over. Given your robotics expertise, where do you see the most exciting or maybe the most challenging real-world applications for robots that learn this way through verbal feedback? And looking ahead, what kinds of robot designs or control architectures do you think would best mesh with these language-based learning methods? Something to chew on.
Yeah, definitely food for thought.
Thanks for joining us for this deep dive, The Learner. We'll catch you next time with more research insights.